Rate law and order of reactions. So we know the rate changes with time. And certain factors affect rate, such as temperature, surface area, concentration, catalysts, and the nature of the chemicals. The pattern between reaction rate and these factors must be determined experimentally. Rate laws deal with the relationships between rate of reaction and the initial concentration of the reactants. In general, the rate of reaction increases when the concentrations of the reactants increase. However, as the reaction proceeds, the reaction rate will decrease because the concentrations of reactants decreases. They get used up as the reaction proceeds. Also, the products that are made get in between the reactant molecules, so you can't have a successful collision. Therefore, chemists use the initial concentrations and the initial rates recorded to figure out the order of reaction and rate laws. The dependence of the rate of a reaction on the concentration of the reactants is given by the following relationship. Rate will vary directly with the concentration of reactant A to some exponent m times the concentration of reactant B to some exponent n. And it gives you here for the following reaction. You'll notice that there's no products, and that's because we don't take into account products. We just deal with reactant concentrations. And the coefficients for the balanced chemical equation, small a and small b, are not necessarily m and n. So you actually have to find out what your exponents are for your rate law. You'll notice these square brackets. If you're not familiar with the square brackets, that's how we represent concentration with symbols. It's also really important to understand that the rate is for a constant temperature. So a lot of time in a question you're going to see at this temperature. It's just extra information because at a different temperature the rate would be different because temperature is one of those factors that affects rate. This relationship can be expressed in a general equation called the rate law equation. The rate law equation expresses the relationship between the concentration of the reactants and the rates of the reaction. So this rate law expression is rate is equal to K, the rate law constant, and times concentration of A to some exponent m, concentration of B to some exponent n. So the rate constant will depend on temperature, and it's constant only under constant conditions. So if you're doing an experiment, the temperature has to stay the same. And K will actually give you information about how fast your reaction is actually going. The rate law exponents will not change with temperature, but you do have to determine them experimentally. So you actually have to run experiments, record your concentrations and your rates. The letter K represents a rate constant, so it's valid for specific reaction at a specific temperature. The values of the exponents establish the order of reaction. Okay, so order of reaction. This describes the initial concentration dependence of a particular reactant on the rate. So if the exponent is 1, the reaction is said to be first order. You can have 0 order too, if the exponent is 0. If the exponent is 2, the rate is said to be second order, 3, third order, and so on. The overall order of reaction is the sum of the exponents in the rate law. So if you've got rate is equal to K, concentration of A to the 1, B to the 2, so first order and second order, then it is third order overall. Try to use the terminology first order and second order rather than 1 and 2. Okay, so the rate constant. The magnitude of the rate constant indicates the speed of a reaction. So if you've got a big K, it happens fast, and if you've got a small K, it's slow. It stays constant throughout the experiment if temperature and pressure are kept constant. So again, you will see in a question either the temperature listed as degrees Celsius or Kelvin. Let's take a look at what these orders mean. If you have a first order reaction and you double the concentration, that means the rate will also double. 2 represents the number double. 3 represents the number triple. 4 represents the number quadruple. So if you triple the concentration and it's first order, the rate will also triple. If it's second order, then the concentration is to the exponent 2. So if you double the concentration, 2 represents double, then the rate will quadruple. If you triple the concentration, 3 squared is 9, so the rate is magnified 9 times. If you have 0 order, then the rate is unchanged and it will not depend on the concentration of that substance. In that case, if you have a 0, you can put it into your rate law equation, or you can leave it out. If you show your work that you've determined that something is 0 order, then you've indicated already that it's 0 order, and then you don't have to put it in. You can have fractions. You can have fractions of a half. So just know that that's possible too. Okay, so here's an example. We have 2 reactants, and we have a whole bunch of products, but it doesn't matter what's on the product side. Okay, so we've got some data. Mmol, millimole. Millimole, that means times 10 to the negative 3. So 4.0 times 10 to the minus 3 moles per liter. So sometimes we just write it as millimoles, so it's just a number. So we're going to have to look at how changing the concentration changes the rate. So the first thing you do is you write the rate law expression using the exponents m and n and so on. So rate is equal to some constant k times the concentration of bromate to some exponent m times the concentration of hydrogen sulfite to some exponent n. So now all we have to do is figure out m, n, and k. So in order to solve for our exponents, we have to compare concentrations within a reactant while holding the other reactant constant, because you can only figure this out if you keep everything constant except for the one factor you're changing. So if you look at the data table for bromate, 4, 2, and 2 millimoles per liter. So trials 2 and 3, because they're the same, will be used to figure out the effect of changing the concentration of hydrogen sulfite. If you look at hydrogen sulfate, we have the same concentration for the trial 1 and trial 2. Those 2 trials will be used to figure out the effect of changing rate of the bromate ion on the rate. So this is how you do it. And you can do it by inspection. I can see that if I double bromate, my rate doubles, And I can see that if I double my hydrogen sulfite concentration, my rate quadruples. However, you do have to show your work, and I'll show you how to do it formally and informally. So, to solve for M, I have to use trial 1 and 2 because that's where the hydrogen sulfite stays constant. And I'm going to compare trial 1 to trial 2. And I'm going to pick this in this ratio because that way my rates will end up giving me a whole number. If I did trial 2 over trial 1, I would get fractions, and it's harder to see the effect if you're doing fractions. It's possible, but some people see the math easier if it's whole numbers. So we compare trial 1 and trial K. So the rate is equal to the K1 concentration of bromate to the M concentration of hydrogen sulfite to N all over the rate K2 concentration of bromate to the M hydrogen sulfite to the N. So I put in my values, 1.60 millimoles per liter per second over 0.80 millimoles per liter per second is equal to K1, we don't know what it is yet, K2, times the concentration of this is 4.0 millimoles per liter over 2 millimoles per liter to the exponent M. And then we've got 6.0 millimoles per liter and 6 millimoles per liter. Now, we can cancel anything that is the same. So we can cancel our K, it's constant, it's the same number. 2 divided by 2 is 1, has no effect. 6 times 6 millimoles over 6 millimoles to the exponent N, it's the same, so we can cancel that too. So if you wanted to, you could skip directly to this ratio of the rates to this ratio of the concentrations. So basically, 1.6 divided by 0.8 is 2. 4 divided by 2 is 2. So then you have to say 2 to what exponent gives you 2? Well, M has to be 1. It has to be first order. 2 to the exponent 1 is 2. So that's how you figure out the value for your exponent M. And you're going to repeat this for N to figure out what that value is. So for N, for the hydrogen sulfite, I'm going to use trials 3 and 2 because the concentration of bromate was constant. And I'm going to put trial 2 over trial 3 because that will give me a whole number. So 0.80 millimoles per liter per second over 0.20 millimoles per liter per second. My constants have canceled. My concentration of bromate have canceled because they're constant. So therefore this is equal to 6 millimoles per liter per second. Oh, sorry, just per liter. 6 millimoles over 3 millimoles per liter to some exponent n. So 0.8 divided by 0.2 is 4. 6 divided by 3 is 2. So what number is n? We're not multiplying, we are doing exponents. So 2 to 1 exponent gives me 4. Well, n has to be 2. 2 squared equals 4. So for this reaction, it is first order with respect to bromate and second order with respect to hydrogen sulfite. So it's a third order reaction overall. 1 plus 2 is 3. So we're not finished yet. We still have to calculate the value of the rate constant K. What you do is you just take the information from one line of the data table and plug it into your rate law expression. So our rate law expression, and you should state it again at the end, I should have done that before this, is rate is equal to K bromate to the exponent 1 and hydrogen sulfite to the exponent 2. So first order with respect to bromate and second order with respect to hydrogen sulfite. So now plug in the values. I'm going to take the values from trial 1. So we have 1.6 millimoles per liter per second is equal to K. Oh, come on. My cat wants to join in the conversation. Bromate. 4.0 millimoles per liter and 6.0 millimoles per liter squared. You are going to get some bizarre units. Don't worry about it. You have to do the same math to your units as you do to your numbers. So let's simplify this on the right hand side. So we will end up with 6 squared times 4. So we have 144, and this is now millimoles squared over liters squared times millimoles over liters. So we end up with millimoles cubed over liters cubed, because you add your exponents when you multiply. And so what you're going to do is you're now going to divide both sides by this 144 millimoles cubed over liters cubed. And don't forget, when you divide by a fraction, and that is what our units are, it's like multiplying by the inverse. So I'll do the number separately from the units. So our K value then is 1.6 divided by 144 So that gives us 0.011. And we had millimoles per liter per second from our rate divided by millimole cubed over liters cubed. So I'm going to say that I'm going to multiply this by the inverse, because that's what's going to happen when you divide by a fraction. It's the same thing as multiplying by the inverse. So what's going to happen is this millimole is going to cancel one of these millimoles, so I'm going to end up with millimoles squared. And this liter is going to cancel one of these liters, so I'm going to end up with liters squared. So our units on our K will be liters squared over millimole squared times S. And you're going to find that every third order reaction will have the same units on their K. All first order reactions will have the same units, 1 over seconds. Every first order, second order, third order, they're always going to have consistent units. And this is how you do it. So don't worry at the fact that they're different, just try it. So now we can write out our proper rate law expression. So rate is equal to 0.011 liters squared millimole squared times second times the concentration of bromate to the first order times the concentration of hydrogen sulfite to the second order at this temperature. So this reaction will not go very quickly because our K value is so small. So I'll do a second example with you. What happens when there's one reactant? So I took this information from an example where they had actually recorded data and then they were going to use it on a graph to plot. You can graph your data also and compare the type of graph to a known set of graphs and determine your rate law that way, because each one will have a specific curve. First, 0, second order reactions. Okay, so here we figure out that our rate is going to be equal to K. We only have one reactant, and that's ethyl bromide, to some exponent. So there's no second reactant to compare to keep constant. So we just compare our rates and our concentration. So just pick two. I'm going to pick trial 1 and trial 2. I'm going to pick trial 2 over trial 1 because that will give me a whole number instead of a fraction. The fractions will work, but looking at 0.2 squared to 0.4 squared plays with people's brains apparently. So, okay, 6.67 times 10 to the negative 6 moles per liter per second is equal to some constant K times 2 times 10 to the negative 3. So I could have said 2 millimoles. All over 3.33 times 10 to the negative 6 moles per liter per second is equal to K 1 times 10 to the negative 3 moles per liter. Okay. So 6.67 divided by 3.3 is 2. Your units cancel. K cancels. 2 divided by 1 is 2. So M is equal to 1. So this is first order with respect to ethyl bromide. So R is equal to K C2H5Br to the 1. So now we solve for K by picking a trial and a rate. I'll pick trial 1, so 3.33 times 10 to the negative 6 mole per liter per second is equal to K times 1.00 times 10 to the negative 3 moles per liter to the exponent 1. So now solve for K by dividing both sides by 1 times 10 to the negative 3. Moles per liter. So K is going to be equal to 0.0000333. And for the units, we had mole per liter per second divided by moles per liter, so multiplied by the inverse. The liters cancel, the moles cancel. S is still underneath, so it's 1 over S. 1 over S, or we can write that S to the negative 1. So all first order reactions, this will be your unit. S to the negative 1 or 1 over S for your units. So rate is equal to 0.00333, 1 over seconds times the concentration of ethyl bromide first order. So there's your rate expression. So now if you know your temperature, if your temperature is the same and you know what concentration it is, you can figure out what your rate will be.